Hello, I'm Umnik. I will be solving second division first round 882 and I will try to explain what I'm doing. Problem A looks like too much letters for problem A. Okay, so we're given an array A. There is a function of a segment which is just sum of absolute differences of neighboring elements in this segment. We want to split into k segments so that the sum of those functions from segments are minimized. Okay, that is a not so bad problem, but like you can do literally what is written in the statement as a DP and it will be a valid solution. But what is intended kind of is to say that well, for every two neighboring elements that will be in the same segment, we are paying absolute difference between them. But we can make k-1 splits, like initially everything in one segment, but we must split it into k segments, so we will add k-1 splits, and each time we do a split, like we remove the need to pay for this pair of elements because we put them in different segments. And so to make the remaining sum to be as small as possible, we want like we have this n-1 things we are paying, and k-1 times we can not pay one of those things. So let's just not pay the smallest things. So among those differences, we will only pay for n-k smallest. And well, we can do it in n-log time. We can actually do it in linear time. So after we read the input, and then we will calculate the absolute differences. So now among those n-1 differences, we want to calculate the sum of k minimum values. The obvious way to do that is to sort the array and then just calculate the sum on prefix of size k. But we don't actually have to sort it. We need to just split the array into like k smallest values and n-k, well, in that case n-1 minus k largest values. We don't care that the order in each part like sorted or anything else. We only care about the sum in the smallest part. And well, I assume there should be a function like partition, but instead we can use function nth element, which will put on this position the elements that should be on this position in the sorted order, and all smaller values before it and all larger after. So after we do that, on position k we will have the elements that should be on position k, so k plus ones, k plus first smallest element, and before it will be the k smallest elements. So after it we can just calculate the sum. And profit from doing that is that nth element function works in linear time, as opposed to sorting that works in analog time. Right, in problem B, it looks like again we have an array and function from a segment, and the function is just bitwise AND of the elements in the segment. And it looks like the whole setting is more or less the same. We again want to split it into number of segments, although the number of segments is not specified now. Continuous groups. Okay. I think that that statement is not the best, because they use the word group, which like can mean just pick them apart, like cover with subsets, and well, despite that the function is defined for a segment, like it's kind of weird. So the only place where they say that the groups should be consecutive segments are this, and it is not even bolded, even though they bold a lot of words. Okay, so we want the sum of ends of segments to be minimized, but having that, we want to maximize the number of groups. And what the problem is about is that we don't want to split the segment into smaller segments, because that would increase end values. Like end value can only decrease when we have more elements. So if we have two segments and then we like merge them in one segment, the value of end will be not bigger than both of previous values, and so that means that like one of the optimal solutions would be to just not do any splits, just have one segment, and the sum of values would be just end in the whole array. But we want to have the maximum number of segments if we still have the same value. consider that the end is not 0. What does it mean? It means that all the numbers we have have those bits set, but then it will be in all the groups we'll create, and since it is not 0, then the sum will be strictly greater than 0. So strictly greater than just the end of the whole array. So if the end of all the numbers is not 0, then the answer is just 1, the maximum number of segments we can have. Otherwise, we can only have segments with 0 end. So now the problem is, we are given an array, we know that the end of all the numbers in it is 0, and we want to have to split it into the maximum number of segments such that the end of every segment is 0. And here I state that we should just do that greedily. Consider the first segment. It will be some prefix in the optimal answer. What if we can make it shorter, but still having the end to be 0? Well, that's good. The elements that we removed we can add to the next segment, and its end can only decrease, but it is already 0, so it will just stay 0. So that's always not bad. So we can shorten the first segment as long as it's possible, as long as the end stays 0. And there is an optimal solution that does exactly that. So we can just cut it and do the same thing further. So the solution will be this greedy. We just start from the beginning of the array, run to the right, waiting while the end becomes 0. At that point, we're saying, okay, we can stop here, just take that segment, cut it, and continue further. If we run to the end of the array and the end is still non-zero, it means that we should just add all of those elements to the previous segment, and we cannot create more segments, because each time we cut the first place we could. Technically, I don't even have to store the values. So I will just read values one by one, and basically this while tries to increase the number of build the next group, and that I will do by saying that, well, start by with having just one value in the first one, and while it is non-zero and I have more elements, I can read the next value, and I must add it to this group. And if I reach and equal to 0, then I should increase the answer. Otherwise, it means that n have reached 0, and but I haven't finished that group, so I have to add it to the previous group. yeah, if the end of everything is non-zero, then I still have to print 1. Yes, they have a thing about arrays and bitwise operations and stuff. So in the beginning we have an array again, and all numbers only have like 8 bits. It looks like we will add new elements to the array. So we start with some array, and then we push back a new element that is XOR on some suffix, on some non-empty suffix, looks like. Okay. What does it mean? Maximum possible strength of A? Who wrote that? So I guess we want to maximize the maximum element of the array. So we can add new elements, and we want to find the maximum element we can make that way. Yeah. Okay. It's not clear right away. So since we only assign like XORs of some existing elements, then every element we add will be a XOR of some initial elements. So let's say that at first we choose some suffix and put it here. And then the next element, like we will again choose some suffix like this, or maybe it will go further. I don't think it matters much. So what is this XOR? We know that this element is XOR on this suffix. So in the end we will have XOR of all these elements and XOR of these elements. But these elements that I use twice, they will cancel themselves. So we will, in the end we will have like this segment. And we know that it will still have this border, like one of the borders of the segment will be the same. If that suffix would go like longer than here, we would have segment like this, but still one of those borders will stay. What about the next one? We could just take the second, but that's not really interesting. Like second and first, that would create this suffix. Like second is XOR on this segment, first is XOR on this segment, so their XOR will be just XOR on this suffix. Also not very interesting. So what if we choose something like this? So we will have both new elements, so their XOR is this segment, and we will XOR it with the suffix here. So in the end we will have like this segment. Well, it seems that everything we can do is just creating a XOR on some segment of the initial array, because like the borders are coinciding, so if we are taking all the elements that we had, well, basically every suffix of new elements will be XOR on the segment with one border here where the last border was, and where the previous border was. And if we take all of them, then it will be just suffix from this point to segment, I mean from this point to the end of the initial array. So we again like have suffix and another suffix, and their XOR is just XOR on segment. So we want to calculate maximum XOR on segment that we can have. And well, that is a standard problem, but here, because the limitations are fairly small, we can even do simpler than usual. We can calculate prefix source and mark all the prefix source that we have. Basically, we just want to choose two prefixes and take XOR of their prefix source to be maximum. So we can just mark all the prefix source that we can have and choose two of them with the largest XOR value. It is tempting to say that we just mark all of them and then try all the pairs in 2 to the 8 squared, but because of multitest, that is slow. Actually, like 2 to the 8 squared times 10,000 tests is not great. I mean, it is like on the border, might pass, probably passes if written right. But instead, we want to like utilize that the sum of n is limited by 10 to the fifth. So like sum of n times 2 to the 8 would be great. So after we write all the XORs we can have, we can iterate over the prefix source, like over all the prefixes, and then for every pair of prefix and the other value of prefix SOR, we can update the answer. So that would work in number of prefixes times 2 to the 8th, so it's sum of n times 2 to the 8th. Or you can just only iterate over the prefix sums that are available. Then there will be like at most n plus 1 of them, so it's also fine. I guess that's easier to write, but it's not a problem in any case. But actually, like, there is a solution in I want to say n log value, like n times the bit length of the number with some bit try. Okay, that actually works. Just not doing 4 4, but like 4, and if I have this number, then do the second 4. That works in okay complexity, because we are doing the second cycle only for the values that we actually have, and there are at most n plus 1 of them. Again, I don't think I have to remember the array, only mark the prefix source that I had. So we reading n elements. After each element, XOR the current prefix XOR with it, and mark that we have it. Didn't even notice it. Alright, problem D. Now we have a binary string of length n, so it's still an array. An operation defined on choosing two distinct integers, two distinct positions, string, and swapping the characters. Okay. Consider m strings where is a substring. Again, array and segments. And we concatenate all of them. All right. There are updates. This update, just flip the bit. Find the minimum number of operations one must perform on S to make this concatenated string lexigraphically as large as possible. So when we want to try to make something lexigraphically maximum, we care about first making the first element as big as possible, then the second, then the third, and so on. The segments we are taking into consideration are fixed, so for every position of the string we know which position of string S is responsible for it. And so we can kind of imagine this as like a sequence of positions, and we just taking elements on those positions from S. So if we can just choose the elements, what would we want to do? Well, obviously we want all of them to be ones, but like if we have some limitations, we just don't know what limitations exactly. Well, we would want to go left to right, and if the element, if we can still decide what to put here when that happens. Well, if the character of string S from which position we are taking it is not yet fixed, then we can decide it. When that happens, well, we will go through our list of positions left to right, and so if we already encountered that position, we fixed it then, and now we are not choosing anything. So we only care about the first appearance of that character, and like the earlier this position appears, the more important it is. So basically for all positions of S, we want to order them by the position of their first appearance in like this concatenated T, and we can calculate it once, just like we are given those segments. Basically we will have a set of all the positions, and when we get like there is the next segment, like the next part we will concatenate to our string will be just those characters left to right, and we can take all the positions that appear on that segment, and left to right they will be like we can determine their first position. So this set we can do that in logarithm time per taking one position, and every time we determine its first appearance for a position, we remove it from the set. So amortized complexity, like the total time we need for it, is just the number of positions times logarithm. For each position we will spend logarithm operations once, and also like q times logarithm, because one more query for one more lower bound in the set for each query, we need to understand that we should stop. Like we exhausted all the positions from the segment. Okay, so now we have an ordering on the positions of the string, and it will never change. And now we can like ignore all this. Basically, we can reorder all the positions, like how they will be read actually. And now we have this. We have to solve like the other half of the problem. We have a string of zeros and ones. We have queries that flip one bit. And we need to say what is the minimum number of swaps we need to make that that string lexicographical maximum. actually, like, there can be positions that do not appear in T at all, and like, kind of, we care about them even less, but it doesn't mean that just putting them in the end would do the same. That's not true, actually. But like, for now, let's consider the simpler case when all the positions are used. And then we have some ones, we have some zeros. All that we can do is some swaps, so we cannot change the amount of ones and zeros. We want to make like graphically maximum string, so we just want to put all the ones in the beginning. And how many swaps do we need to do that? Well, we know how many ones we have. We can maintain that. So we know on which prefix we should put ones. On positions where there are already ones, it's all good. On positions where there are zeros, we need to swap that zero with some one from the suffix. And we know that we had one on the suffix because it is like, we know the total number of ones is correct. Like, we have chosen the length of the prefix to be the total number of ones. So the answer would be just like the number of zeros on that prefix. Now, what if we have positions that do not care at all? Then we want to put as much ones as possible, and on all other positions we want to put zeros. So okay, if the number of ones that we have is not greater than the number of positions that we care about, then it's the same. We still have to fill that prefix. But if it is bigger, then we can make all the characters to be ones, and to do that we only need to fill the positions that we care about with ones. So we need to calculate the number of zeros on the prefix of length that is minimum of the current number of ones and the number of characters that we care about at all. And that's problem D. Right. I didn't explain how to actually do that. We can have like Fenwick tree that will store ones and zeros, and we will also maintain just the sum of ones, although we can just take it from Fenwick tree, doesn't matter. Store the number of ones, and then like on prefix we want to take the sum, basically. It's not. So in the first part, we will read those m segments and construct the order. So on the segment, I want to take the first unused element that is after L, and if it is before R, then it is on our segment and we should assign the next position to it and remove it from the set. If it is after R, then we just stop. We exhausted all the indices on the segment, and for that I inserted n in my set so that I always have an element that is after everything, so I don't have to make additional case for when I reached the end of the set. Let's put -1s in the beginning so that if element is unused, it will have position -1. Alright, so now I want to just re-enumerate all the whole string. I guess it will be easier to say that the positions that we don't want also have IDs, so that again we don't have to do anything special for them, but I will store the that actual number of positions that I care about is just k. So the position I actually is AI's important, by importance, and so we will put the character that was on position I to this position. Yes, it will be easier if I use integers. So if it is 1, then I need to increase the number of ones and turn it on infinite. Then in each query I am asked to flip one bit. The actual position where it is stored is A of V. And now if it was 1, then the number of ones will decrease by 1, and I need to subtract it in Fenwick, otherwise the number of ones will increase by 1, and I need to increase it by 1. Flip S of V. And now just calculate the number of zeros. Maybe it would be better if I store zeros in Fenwic. Let's do that. Not important. Okay, let's stick with ones. So the length of the segment that I should care about is normally it would be the number of ones, but if the number of ones is more than k, then just k. I just want to put ones on all the positions that matter. And then the answer to the query is the number of zeros, which is the length of all this prefix, minus the number of ones, which is this. Should be. Interactive problem. Have n hidden integers from 1 to 4. Must determine all the AI. We can ask queries. Asks 3 distinct indexes, and if the triangle with those sides exist and have positive areas, and we will get the area. Otherwise, we can ask 5,500 queries, and n is up to 5,000. Also, there is an option that it is not possible in German. The interactor is not adaptive. It kind of feels like, since the values are so small, like I should look at what would be the responses for all the multi-sets of values. There are not so many of them, like something like choose 6, 3. So it's 20. Yeah, 20. It's not very small number, but I guess many of them will be like degenerate, probably. Okay, let's see. So what will actually be outputted is 16 times area squared. So there is a Heron's formula for the area of the triangle, where P is half a perimeter. So if we have 16s squared, then we remove the square root and multiply all the four multipliers by 2, so we will have like a plus b plus c times minus a plus b plus c times a minus b plus c times a plus b minus c. So that's the number that will be output. Okay. Okay, 1 1 1 3 1 1 1 3 1 1 2 1 1 3 and 1 1 4 all 0, because the triangle inequality doesn't hold. 1 2 2, it's 5 3 1 1, so 15. 1 2 3 and 1 2 4 zeros. 1 3 3 7 5 1 1 35 1 3 4 0 and 1 4 4 9 7 1 1 63. All right. 2 2 2 6 2 2 2 2 2 3 7 3 3 and 1. That's 83 again. Well, that's the first repetition. 2 2 4. Well, not considering zeros. 0 2 3 3 8 4 2 2. So it's 128. 2 3 4. It's 9 5 3 1. 9 times 3 is 27 times 5 135. So what's next? 2 4 4 10 6 2 2 240. 3 3 3. I mean, it should be like this times 3 to the 4th. 3 3 4 3 4 4 and 4 4 4. This 10 4 4 2. 11 5 3 3. That's yeah. And this will be the biggest of them, but I guess I should be able to say what that is. It's like 3 times 4 to the third, 3 times 64, oh, 4 to the fourth. So it's 256 times 3, 768. Alright, so we cannot distinguish zeros, and we cannot distinguish 1 4 4 from 2 to 3. All the others are unique values. When I would not be able to determine obviously if n is 3, then okay. It kind of feels like I should just ask all the combinations on like first 10 or something. If we will have something that we can determine. Okay, yeah, I'm on first 10 elements. There should be 3 elements that are equal, because otherwise we only have 4 possible values. If each of them appears at most 2 times, there is at most 8 of them. Alright, if those 3 equal elements, well, first of all, I can determine what are those 3 equal elements, because all the answers for 3 elements are different and different from everything else. So if I get one of those answers, then I can just understand immediately that those 3 elements are equal and what are they equal to. And then if I have if those values are not ones, then I can just take two of them, I know both of them, and I can ask with every other element what's the area, and by the result I will be able to determine that last element. So that's great. So the only bad case, well, if n is big enough. If n is not very big, like less than 9, I can just ask all the triplets, and I can try all the 4 to the n's options for them and see which are consistent. If there is exactly one of them, then that's the answer. And I also will probably do that for like when I ask all triplets of first like 9 or 10 elements to determine them, if possible. But okay, what if I have a lot of ones and not a lot of everything else? Like, I will be able to find all the ones. That's great. But I will not be able to distinguish all larger values just by using two ones. I need to compare them with themselves. Well, after I know all the ones, it doesn't make sense to query them with two ones. So I can just left only one, and kind of do the same thing. The only issue is that I don't want to do the linear search again. Like the number of triangles on the 9 elements that I will need to ask first is like choose 3 from 9. So that's 9 times 8 times 7 divided by 1, 2, 3, and that's like 3, 4, 7, 84. So that's very small. Like the number of queries that I have is like 5,000 for the linear part plus 500 more. So I don't want to do the linear part again, but it kind of seems like if I choose the random order of the points and like ask the first linear search in that order and stop once I have enough like big elements on which I can run the same thing and determine everything. Like either there is just very small number of them, or I will stop quite fast. or maybe it doesn't even matter. Yeah, I don't have to do the random thing. Just stop while once I have enough. So like I wasted like 10 queries, and now I can like for each query either it it is a one and I have determined it and that's great. I can just remove it and forget about it, or it contributes to that 10. After reaching 10, I will just stop and start again. Um, yeah, that works. They should be sorted. Come on, why did you do that? So if n is small, I should just run like solve small. Okay, so thankfully there is no multitest. So I guess I will just have function fail that will print that it is impossible and terminate the program immediately. Or is it, yeah, exclamation point? And so at any point I can just call fail if I need to, and I know that the execution will stop. So I'm doing either like solve small or I will iterate over all the triplets of first 9 elements, and if it turns out that they are all equal, and I can determine that, then I will stop this iteration and say, okay, I found 3 equal elements. Now, if there are not ones, then great. I'm just doing linear search and saying what there are. Otherwise, I'm starting to do linear search, but waiting when I can find like enough not ones to find 3 equal among them, and then do the actual linear search. I know that I have to find triplet of equal elements. Now, if the values that I found are ones, then I will try to find, I guess, 7 elements that are not ones by doing linear search. So I will not ask about the elements I already know that includes, well, right now X, Y, and Z, but also that will include all the ones that I will find here. I will just copy that cycle to use it further. So okay. can happen that I just have not enough elements that are not ones. And in that case, I should add one of the ones there so that I can determine something with that one. And I will just call solve small. If it fails, then it fails, otherwise I will find the answer. Otherwise, I have found 7 elements that are not ones. So among them there will be 3 elements that are equal and not ones, and I will find them. So I'm doing this thing again. But yeah, I should have written that differently. Doesn't matter. And when I say A, it should actually be... Do I even need a vector of... Not really. So that... Okay, I kind of messed up big time. This vector I will only create if I need it here. Okay. Then here I can find the triplet, but only among the elements of B. Okay, so at this point I finally know that I know the ends of x, and for x, y, and z they're equal and they're strictly greater than 1. And so now I can just iterate over all the elements, and if I don't know the answer yet, then query And now I need like some functions that will say what is the correct value for ans I. Determine sort if I know that the area is S and I have two sides with length that is equal to ans(x). So that should be it. Okay. So now what's left is to write solve small and write determine sort. Okay, so in solve small, I will iterate over all the triplets, ask about all the areas. So let's say that we have these 3 answers. Now I will iterate over all the 4 to the nth power possible values, calculate the actual values for them, and compare them with answers. And if the comparison is correct everywhere, then it's possible, it's a viable option. I can iterate over them as just bit mask, but of length 2n, because actually my options are not binary, but there are four options. Well, let's not create that many vectors. Instead, we'll create it once here. Okay, so those are like perspective values that I want to check, and now I will iterate in the same order over all the triplets and check if all the answers are what I expect of them. So if there was an answer that does not is not equal to the one that was told by the interactor, then that option is bad. Otherwise, it is good. And if it is the first good option, then like, okay, we remembering that it is a good option. Otherwise, we have two good options, so we cannot determine unique answer, so we will print fail. Okay, like here, maybe I should put all three XYZ so that I know that they're ones and I will be, like small will be able to determine that. Yeah, let's do that. That's more safe, and I think it should be like it shouldn't mess with the number of queries too much. The size is still like bounded by 9, so it's fine. Is it guaranteed that the answers are consistent, like the answer exists? I guess so. So we can assert that it is not -1. And so I found the answer, and now I need to put it in ans array at correct positions. And determine sort. Now the area, we know the length of two sides and they're the same. So we will iterate over the 4 possible lengths of the other side, calculate the area. And if it is equal to S, then say that it is answer, but just for sanity check, if there are 2 possible answers, that shouldn't happen. So assert that it is still -1. Okay, so I wrote that, and I don't want to test it by hand. Like, no way. And I also don't want to spend time writing the interactor, so let's just get wrong answer 1, and that would be great, right? That's even worse. did the calculations correct. Looks like it. Okay. latency issues. It would be funny if it's in some those nested fors somewhere wrote wrong variable. Like in this case, I should not do this. I feel like I did something wrong, but whatever. Oh yeah, more arrays and bitwise operations. Amazing. Problem F. So there should be an infinite sequence of positive integers. The first n numbers are given, and then next values are defined as bitwise OR of two neighboring elements and back. Okay, whatever you say. Each query is a positive integer v, and the answer to the query is the smallest index I, such that ai is greater than v. Right. So the next element will be OR of this two, then OR of this two, then OR of this two, and so on. Then element with ID 2n minus 1 will be the OR of these two elements. And then the next element is an OR of this element. And like the next one, which is the OR of the first two. So it's kind of like OR of this element and first two. The next element will be the OR of like this element and this element, so it is an OR of first three elements, the next three elements, and so on until we reach the end, where we should take like an OR of this and this, which will be like OR of last two elements and first two elements. Then we take OR of this and next element, which is an OR of this three. It feels like, so first we have like first n elements, then n minus 1 pairs, then triplets, but starting from like n, and we kind of on circle, and we end with a triplet that ends in n. And the next element will be like one longer. All right. So we kind of, like for each query, we want to find the shortest segment with or equal, not equal, strictly greater than that value, and among them like the leftmost one, and also we are on circle, and the segments that go through the circle are kind of better. But isn't that like for a fixed left border, for example, if we move right border, then the OR ends on the OR changes only like log the number of times, because we can only turn off turn on some bits. So there is actually like only n log c interesting segments, and we can find all of them, sort them by value, And then each query is just a lower bound. I mean, for each segment, I need to understand what its position is. But I don't think it will be much of a problem. Sounds correct to me. And like the segments are actually listed, sorted by length and the right border, and right border can be like after second element and then third, fourth, and so on till ends. After the first element, we can't have a border because first and last, first and second, like always together. But all others we do have. That sounds correct. And to find it, I need like some kind of I guess like data structures that allows me to take or on segment, and then I will do like binary search on it like for next position that changes. I don't actually have to do binary search. Some kind of binary jumps, the same thing. Well, it's unlocked should be okay. There are two places where I need unlocked. I can write that in 20 minutes. It sounds much easier than problem E. Will be interesting to look which one solved more. Okay, so now I have a sparse table, basically for every segment of length power of 2, I know the value of R. So I should first sort by position, then I will store only the records, and then I will flip each pair so that I can just do a built-in upper bounds for query. So yeah, in the beginning I should say 1 and A1. And now for all right borders, except right border 1, I copied the array so that when I do cyclic segments, I'm just going through the split in the middle, so the right border will be in the second copy, but I should ignore right border with that should be in like after the first element. So it's n plus 1. Okay, and now for this right border, I will iterate over the I will kind of do while true. Okay, I will try to find the next point, like increasing length, and with increasing length moving left border to the left. I want to find each place when I move the left border by 1, the OR changes. So the current OR is like 0 if I have empty segment. And now I will move it. What I was thinking about that there is some not nice things, like I don't have the okay, I have all of them, so I should start here like from +2 and here inclusive, so that's yeah, that's fine, never mind. Okay, I have all those segments. I only don't have segments that have right border right after the first element. All good. Okay. And now like binary jumps that are implemented like binary descent. If I cannot jump by that much, I shouldn't. If the value on the segment will be like this, and I will OR it with W, and if it is not the same, then like this jump is too big. So I want to find the last jump that will still be the same, and then do one more. Okay, now this is a new value, and I need to calculate what is the position of that segment. So the segment from L to R, so it has length minus L, and my segments are sorted by length, and inside by the right border, which iterates from 2 to n. So there are like groups of n minus 1. So the actual ID is length minus 1 multiplied by n minus 1 plus the right border, but in like minus n, because I shifted like the actual right border from 2 to n should be correct. So if I'm looking at the segment 0, 2, this will be 2 minus 1, 1, n minus 1 plus n minus plus n plus 2 minus n. So it's n minus 1 plus 2, n plus 1. That's the first segment that is there. Should be correct, yes. Alright, now we have all of those. Now just sort them and only leave records. And now in each pair I first had position then value, now swap them so that the answer for query is just like lower bound. That's interesting. Like I explicitly a0 zero indexation is hard. Yeah, looks correct. This should be bigger than maximum n multiplied by like 30. So it's 6, yeah, 6 should be enough. And on the other hand, it fits into the memory limit. There is like a chance of time limit, but I don't think so. All the logarithms are kind of not that heavy. 1.7 and time limit was 3. So almost half of time limit. So yeah, log n log c only like here. This while true does like log c operations, and here I'm doing log n for binary search or binary jumps, whatever you call it. So this log c is like actually 30, maybe like 31, and this is actually just f4. And then here I'm searching an array of lengths up to n times 30. So it's n times 30 times log of z. Yeah, everything else is like this is just linear from n log c, and this for every query just lower bound. Yeah, that makes sense. It's not even hard. Like, it's more or less impossible to do anything wrong. But it's an unusual interactive problem. Like, and also there is like school geometry or something. But you can Google formulas, so it's not that bad. Like, you don't have to remember the formula for the area or triangle, but I guess that might be not great for someone. But yeah, it's not hard, but it's kind of tedious to implement and even more tedious to test. But genuinely, the problem set was fine. This is a fun idea. Like, the problem is kind of mocking the concept of like those DP problems, like split into k segments. That is like DP and a lot of DP optimization problems look like that. But if the limitations are so small that the solution that you're mocking is fine, is it actually worse? Like, if you know that either this is unfunny joke and you will just not understand it, and the statement is too convoluted for Div2a, or you understand the joke and then it gives you a viable solution. Like, you can just write a DP and it will give you the right answer, even though there is an easier solution. Like, why not make it like 10 to the 4th? I don't know. This is a okay problem. Actually, I don't dislike it. Like, usually when there are like segments and bitwise operations, it's just super boring. But yeah, the twist is nice. Like, there is an obvious optimal solution, but you then need to make it worse, but not make it worse. It's interesting. That's a weird problem. I don't like it. It kind of feels like they had problem F, and then they needed problem C for some reason. And like, the setting is very similar, and then it is reduced to boring, and like understanding the reduction is kind of tedious. Again, not hard, but not kind of it is too hard for the target audience, I would say, but it's not too hard. It's not hard enough to be an interesting problem. So like, I don't see for whom this problem is. Like, it is too easy for strong participants and too hard for not so strong participants. Problem D, it's fine. Not great, but it's more or less natural, and it is split into two completely independent problems. That is kind of nice, but like, it is does not unexpected for such kind of problem. Like, the updates, like basically everything is done in string S, and T only exists to like, add this another half of the problem. It's not very unnatural, but also not very great. Problem E. I think the problem itself is nice, and it would be, I think it would be good in like ICPC contest where you have like a lot of time not using the computer, so you have time to like, figure out all the weird cases, and then write the code, and then debug it on paper. But in short personal round, it's kind of, yeah. Problem F. If there were no problem C, I think it would be good. But together, like, they look like the contest preparation was not going so smoothly. think they have like very similar vibe. But I guess Problem F is good, even though like it is simpler than F for me, and I guess for a lot of people. Well, that's that. Thanks for watching. Bye.